In this video, we will be embarking on a retro programming adventure where we will explore the Label Assembler Development System, also known as LADS, to write code in assembly language on a Commodore VIC-20 computer. The assembler software was published as a type-in program in a book, The Second Book of Machine Language, published in 1984 by Compute magazine, and had code listings for the Atari, Apple II, Commodore 64, PET, and VIC-20 computers. I thought the Commodore VIC-20 was the most interesting of the computers imported in the book because of just how little memory it has. The VIC-20 out of the box had just 5K of RAM. We are going to need to expand it to at least 13K to use the assembler software, however. But first, let's acquire the LADS assembler software like it was 1984 by typing it in from the book. Before we start keying in the source code for the assembler, we need to key in a program called MLX. This program lets me type in the assembler. It took me only about 15 minutes to type this program in and about 45 minutes of fixing it. I tested each function of it thoroughly before I committed myself to entering the approximately 5,800 sets of 3-digit numbers. I really want to make sure I'm ahead of this once. Before we start typing in the LADS assembler from the book, however, we need to upgrade our VIC-20 with at least an 8K expansion module. Let's take a look. The VIC-20 out of the box has this 5K RAM with it. 1K, the blue, is used by the operating system, basic, and just about everything else that makes the machine go. The orange half K is the RAM put aside to render the text on the screen. This leaves us just 3.5K for basic. That's the green part. The LADS assembler, once keyed in, is just shy of 5K, so clearly it's not going to fit into the unexpanded VIC. Once we pop an 8K expansion in the system, however, and restart the VIC, the memory layout will now look something like this. The good news now is that basic is much bigger. 3.5 plus the 8K gives us 11.5K for basic. The machine now clearly has enough RAM to fit LADS in. The problem though is basic took it all, and we will be using basic to key in the LADS assembler. As we're keying it in, the basic is moving into the RAM from both sides, and we will most likely corrupt what we're keying in. The instructions in the book tell us to type these two poke commands to solve this problem. These commands will tell the VIC-20 to make basic smaller. Now we have 6K available to basic and 5.5K free to type in the LADS assembler. Here we can see we have 11,775 bytes of free memory. If we type in the command print free 0, we should see the same number-ish. And we do. So now let's put those two poke commands in to shrink the size of basic. Now let's print the free memory again. And here we can see basic is 6K. Awesome. Now we can load and run MLX and start keying in the assembler. The book tells us to use the values 11,000 and 15,985 for the starting and ending addresses. I added this little piece of code myself. This will clear the memory with all zeros. This makes entering the data into multiple sessions much easier, as you can clearly see where you haven't typed in data yet. So we're going to press Y for this. And now the pain begins. Each row in this MLX source code is 6 bytes of data followed by a checksum. If you get the checksum correct, you get a nice little bell sound and you can move on to the next line. If you make a mistake, you get to hear a buzzer sound and you have to rekey the entire line again. So let me kind of show you how this went. The bell sound is great. I can move on to the next line. I made a mistake, so then you have to rekey in the line. Perfect. As you can imagine, this is quite the test of patience and will to get this done. Each page takes about 15 minutes to key in, and there was, I think, like 16, 17 pages of it. So I did it, of course, over multiple days and multiple sessions, but I did eventually get it done. Now you're probably thinking, well, hang on a second. That says that's the Commodore 64 version, and you would be right. The instructions for the VIC-20 version are to key in the Commodore 64 version, as I did, and then there's yet another page which contains changes to the 64 version that morph it into the VIC-20 version. Luckily, that page, as you can see here, only has 18 or 20 lines of entries on it. So that took like just, I don't know, 5 or 10 minutes. Wasn't a big deal. But now I have the 64 and VIC-20 version of LADs, all for the price of one, I guess. Oh well. But now let's program some assembler on our VIC-20 with our new LADs assembler. So this VIC-20 has a 16K expansion cartridge plugged into it. Obviously, it's in an emulator. And this gives us almost 20K free of basic memory to work with. The way that you write assembler code for the LADs assembler is just by running it in BASIC, and you save it as a basic program, and then you invoke the assembler. One of the cool things about doing it this way is you can use any basic wedge or DOS wedge utility. You can also use cartridges like the Programmer's Aid, which is a basic wedge which gives you extra commands in BASIC, such as renumbering your code or auto line numbering as you type. But we're just going to go with plain vanilla basic V2. So let's start by writing a super duper simple program so we can explore how LADs, the actual assembler, works and what the process is. So the first line of code we're going to write sets the program counter to hex 4000 or 16384. This is where a program is going to assemble to, and this is pretty typical of most assemblers to have this command. We're going to load the accumulator with a value of 10. And then we're going to store that value of 10 into hex address 900F. This is the address that controls the border color and the screen color. This, of course, will return from subroutine. So when we call this with a sys command, this will bring us back to the ready prompt in BASIC. And finally, we end with what's called a pseudo opcode, which they start with a dot. And this is a command specific to the LADs assembler, and it tells us that this is the end of the program, and it's in a file called main. It's kind of strange you have to name your file here, but this will make a lot more sense later on when we start exploring multi-file projects. So let's save this as just a regular basic program. Okay, now that it's saved, we can load our assembler. And the way that this assembler works is really interesting. Before you do anything, you have to type new. This frees BASIC up and just clears tons of space in memory for the assembler to work. What you need to do is clear the screen, type in the name of the file that you're going to assemble at the very top left corner of the screen. Press Shift and Enter so you go to the next line without actually running it as a command. Because if you run as a command, you'll get like a syntax error or something. And then we call the assembler with sys 11000. And if you remember, 11,000 is where we started typing it in the MLX program. And here you can see LADs started. It told us that our program is going to start at 4000 and it ends at 4006. And it's assembled it. Now, you might think at this point, it must be in memory. We can just run it with sys 16384. But as you'll see, this won't do anything. Just goes to ready prompt, didn't change the background. Clearly, your program didn't work. Why is that? By default, with no options, as we wrote our extremely simple code before, LADs will assemble the code, goes through the whole motions of checking it, the 2 passes or 3 passes, but it won't produce any output unless you tell it to. So we're going to load our program in and instruct it to output into memory. So we're going to add a line of code at 15, and it's a new pseudo operand called .o, which stands for output. So now when we run this to the assembler, it will not only just go through the motions of checking our code and assembling, it'll actually write the assembled code into address 4000 or 16 through 84. So let's save it and run it through the assembler again. I'm using the @: feature of the disk drive to override it if it exists. And now this time you'll see the .o in the output, but now it's in memory. So we should be able to run it with sys 16 through 84. And as you can see, our border colors were set and we're back at the ready prompt. So that's the super simple a cycle of creating a file and assembling it. Let's take a step back and bring that source file back up and talk about another way to output assembler code. So instead of the .o command, we can use the .d command. Actually, you can use both at the same time, but we're going to just use one of them. .d says, instead of writing the assembled code to memory, write it to disk. So we can write it to a file. We will call this file main $4000. So let's save it and run it through the assembler and see what it does. Excellent. You'll see kind of in the middle of that block of text that says main $4000. That right there is when it wrote it out to disk. So let's take a look at the disk directory and load it and run it. There's our program. And voila, it works. Going forward though, we're just going to output it to memory. But what's neat about that feature is you can write your assembler and you can target, for example, memory just 11,000 where the assembler sits, or maybe an unexpanded VIC or different memory configurations of VIC using an assembler, using this configuration of the VIC-20. We're going to create a file that contains a subroutine that we can call from the main file that we've already created. This subroutine is going to let the user, or let our calling routine rather, pass us in a screen color and a border color. We're going to combine it and then we're going to set it into 900F. This will be useful for a program later on, and it gives us an excuse here to create a subroutine and show you how that works. So let's get started. If you look in a VIC-20 program's reference guide, you can see that this one byte controls the screen and the border color, and a flag called the inverse color, but we're just going to set that to 1. We're going to create some memory locations to allow our calling routine pass us a screen color and a border color. We'll do that down here. So SC color is a label that's going to define a memory location. That's a byte, and we'll make it 0 for now, but we will be able to set that to whatever value we want from our main routine, from our main file. And BD color is the border color that we could set from our main file as well. So the first thing we're going to do is we're going to load the color, the screen color, into the accumulator. If you look at a color chart, you can see that the values range from 0 to 15. And the reason why that is because that's what you can fit in 4 bits. If we pick the very, very bottom color of light yellow, it's 15. And 15, if you using a programmer's calculator, you'll notice there's 4 ones. It's 4 bits in binary. So it looks like this. But we need to move those to the far left. We can accomplish this using the ASL opcode, which is the accumulator shift left. Every time we call this opcode, it takes the value in accumulator, it moves, it shifts it all, shifts everything over to the left, and then throws a 0 on the right side. So if we do this 3 more times, or a total of 4 times, we get the effect we want. So here's how we do that. In LADS, we can put opcodes separated by colons instead of having one on each line. This is a perfect place for that because it's very clear what we're doing in one line of code. It's really fits really well on this tiny 22 column screen, and it makes it very readable. Well, now we want to mix in the border color. So our border color, if you look at our chart again, goes from 0 to 7, and we'll pick the far right color, which is yellow. Okay, and we're going to come down here and imagine what that looks like. And using our calculator, if we type in 7, we can see that it's 3 bits. It's 111. These 3 ones here. So it looks like that. So we need a way to combine these, and we do that with the ORA operator, the OR with accumulator. So this is going to take the value in border color, which we're going to pretend is a 7, and it's going to OR it with the value in accumulator, which is our screen where the bits shifted over. And what ORA does is it goes through each pair of bits in these 2 bytes, and if either one of those bits is a 1, it comes down into the new value. So 1 or 0 is true, is true, is true, is true. Both are 0, that's going to say false. And again, only one of these has to be 1. So there it's combined the numbers together. Cool, now we're getting somewhere. And it stores that result in the accumulator. So now our accumulator looks like this. But now we need to set that 3rd bit on. Well, we can use OR again, and we're going to pass in an 8. Because that's bit 3. And again, we can use our calculator to look at that. So if we were to go into the binary field and try to set that 3rd bit, it's an 8. Awesome. Or bit number 3, I should say. Remember, it's 0, 1, 2, 3. It's 0 based. It's not the 3rd from the right, it's bit 3. So we're going to OR that with an 8. And then that will give us all 1s, and that gives us our color. We take this value, and we store it in 900F. All right. I noticed that we have spelled main wrong. It should be main, not man. Program looks pretty good. Let's save. Excellent. So now we want to link this with main. So you'll notice that this ends with .end of main, but we saved it as set color. We're going to change main to end with this file, and then this file ends with main, so it creates a circular chain, and when the assembler realizes that it went back to the first file, it stops, and then it continues on and generates its output. So we do need to modify main. So main, instead of .end, we use .file. .end can only be used in the last file in the chain. So if we had 4 files, the first 3 files would end with .file, and then a 4th file would end with .main and the name of the first file, creating a chain of files. Now let's also modify this code to call our new subroutine. Okay, so we're going to load 15 in for a screen color, store it in that screen color byte that we allocated in the set color file. We're going to load 7 into the accumulator and store that into the border color. We're going to add a line 35. That's going to jump to that subroutine, which was the label we called set color, which is the top of the file, to do the work. And now if we look at it, then we return. And that's it. So let's save this and give this a shot. It looks like it might have worked. Let's run it and see what it looks like. Well, that clearly didn't work. Clearly there was a bug in our set color file. When we called the sys command, it didn't function the way we thought it was going to. Let's load it up and take a look. Ah, I see the problem. We didn't return from subroutine after line 90. All right, let's give this a shot. And there we are. We're working with our beautifully, horrifically ugly colors that we've set in our test file. Hope you enjoyed my little presentation of the labs assembler in the VIC-20. And thanks again so much for watching. Take care all.